how that affects changes of state of matter. So just as a quick review, if you start with a solid and that solid becomes a liquid, that's known as melting. If that liquid becomes a solid, it's freezing. Okay? If a solid becomes a gas, like what happens with carbon dioxide with dry ice, that's called sublimation. So solid to a gas is sublimation, gas to a solid is deposition. Then if that gas becomes a liquid, it's condensation, while if a liquid becomes a gas, that's called vaporization. And what you should notice on the right-hand side, this is what's called the heating curve. So if you look at it, if you start at the very bottom, that solid is heating up to 0 degrees. Okay? Once it's at 0 degrees, it plateaus, and it plateaus because the solid is going from a solid to a liquid. In order to have a state change, what's actually happening is you are breaking the intermolecular forces, which we studied, that are holding those molecules together. So that's why the temperature does not change. Then, when you're at 0 on that far side as a liquid, then the temperature is going to increase if you put in more energy. The temperature is going to increase until you reach 100 degrees Celsius. Now this is for water. It's going to be different values for other compounds. Once you hit 100 degrees, then you plateau again. And that's because the liquid is becoming a gas. Now notice this plateau is much longer than that for melting. And the reason why, when you melt, you do break intermolecular forces. But when you go from a liquid to a gas, you have to break all of the attractions between molecules. So as a result, it takes a lot more energy for a substance to boil, to go from a liquid to a gas, to be vaporized, than for it to melt. And then once you're at the end of that and you're completely a gas, then the temperature of the gas can continue to increase. So that's a heating curve. So let's talk really quickly about melting and freezing. In order for a substance to melt, a solid to melt, heat must be put into the system. Okay? And so that makes it endothermic. The heat is going to be positive. For a liquid to become a solid, okay, heat is going to be released. And that happens with freezing. That's why heat is released when you have a freezer. That's why you have a fan under your fridge in order to release some of that heat, or else your fridge would get overheated because the process of going from a liquid to a solid releases heat. So let's talk about a term that helps us in order to determine the heat that's involved in this melting and freezing process, and that term is your heat of fusion. So the heat of fusion is the energy that must be added in order to convert 1 gram of solid to a liquid at the melting point. So we're going to use this value, which will always be given to you, in order to calculate heat that's involved when, for example, ice melts. Okay, so if I have 15 grams of ice, I'm going to convert this into joules by using my heat of fusion. So I'm going to put grams on bottom, joules up top. Then the heat of fusion is 334 joules for every 1 gram. And so I get the heat that's required, or heat that's absorbed, to be 5,180 joules. Okay? So let's look at this for your other state changes. Specifically, let's look at vaporization and condensation. Okay? In order to calculate the heat that is involved with the vaporization or condensation process, okay, we're going to be using this heating curve a little bit later on, so I just wanted to include it there for you to see what's happening. You're at that top plateau right there where boiling is happening. Let's actually calculate this. Well, we need to use the heat of vaporization for this. And so the heat of vaporization is the energy that must be added to convert 1 gram of liquid to a gas at your boiling point. And so it's nice, I like the heating curve because you can actually see these processes. That plateau at the very top, that is the heat of vaporization. So let's actually calculate the amount of heat that's needed to vaporize 33.8 grams of water. So if I'm given 33.8 grams of water, if you notice, your heat of vaporization is actually in kilojoules per mole. So I've got to first convert these grams into moles. So I'm going to put grams on bottom, moles up top. I'm going to put the molar mass of water on bottom. Now I'm in moles. Now I can use my heat of vaporization. So I'm going to put moles on bottom, kilojoules up top, and then I'm going to put the 40.7 over 1 mole. All right? So now what I get when I do that math, I get 76.3 kilojoules of heat is required to vaporize that water. So in this lesson, I'm going to be talking about specific heat. Now, the specific heat is the amount of heat that's required to raise the temperature of 1 gram of a substance by 1 degree Celsius. What your specific heat allows you to do in layman's terms is to calculate the amount of heat that is involved in raising or in lowering the temperature of a specific amount of a substance. So we're finally able to relate the concept of temperature, which we looked at in the previous lesson, and energy or heat that we looked at in the previous lesson. So the formula for specific heat is Q, which is your heat. Heat equals your mass, M, times your specific heat, which is represented with a capital C, times your change in temperature. Now, your change in temperature is your final temperature minus your initial temperature. So, for example, if you start off at 10 degrees Celsius and the temperature increases to 20 degrees Celsius, the change in temperature would be 10. However, if you start off at 20 degrees Celsius and you decrease the temperature to 10 degrees Celsius, the change in temperature will be negative 10 degrees Celsius. So let's look at an example. Here it asks you to calculate the heat, so you're searching for Q, you're going to calculate Q. That equals, well, it gives you your mass, which is 50.0 grams of water, times your specific heat, which is 4.18 joules per gram degrees Celsius, times your change in temperature. Well, your temperature changed from 17 degrees Celsius to 37 degrees Celsius. So that's a change, 37 minus 17, that's a 20 degrees Celsius change. Notice that I put 20 point, and the reason why is you might be tempted to say that 20 only has one significant figure when you're doing your final calculations. But since you're subtracting there, 37 minus 17, your rounding should be based on decimal places. So I want to include the 2 and the 0 for significant figures. So when you multiply those together, what you get for your heat is 4,180 joules. Well, I want to round that to 2 sig figs, so that's going to round to 4,200 joules. So a 590 gram brass candlestick has an initial temperature of 98 degrees Celsius. If 21,100 joules of heat is removed from the candlestick to lower its temperature to 6.8 degrees Celsius, what is the specific heat of brass? So you've got your formula, Q equals mc delta T. We're given my Q now, we're given my heat, we're given my mass, and we're given my change in temperature, and they're asking you to solve for specific heat, or your C. The only quirky thing about this problem, and the reason why I chose it, if heat is being removed from a system, the word removed implies that instead of being positive, which means it's being added, your heat is going to be negative. So here, instead of 21,100 joules, it's going to be negative 21,100 joules, okay? So that's my Q. My M is my mass, so 590. I don't know my C. And my delta T, which is always TF minus TI, so final minus initial temperature. So that would be 6.8 minus 98.0 degrees Celsius, okay? So when I subtract, notice when I subtract my temperatures, the difference is going to be negative, okay? The negative temperature, when you end up dividing to solve for C, because you're going to divide both sides by 590 and by your change in temperature, the negative from the temperature and the negative from your heat will cancel. And that's really important to note because your specific heat will never be negative, ever. So if you happen to get a specific heat that's negative, that means you accidentally forgot to make your Q negative, or you forgot to do T final minus T initial, and instead you did T initial minus T final. Okay, so when I do this, I get for my C, my specific heat, 0.39, because I want 2 sig figs. My units are going to be, well, I divided heat, which is joules, by mass, which is grams, and by change in temperature, which is degrees Celsius. So my specific heat is 0.39 joules per gram degrees Celsius. So if you ever see the word remove, it implies that your heat is going to be negative. Now, should they have written negative 21,100 joules? No, because by writing it was removed, then they're all good. So if you get a problem where your Q is negative, you have two options, right? So if you got an answer of negative 21,100 joules for this problem, right? If the problem were flipped and you were solving for your Q, you could either say the heat change is negative 21,100 joules. Or you could say that 21,100 joules of heat is removed. You can say either because one actually has a negative and one implies a negative. So that's why I wanted to bring this problem up, just to prevent confusion.